All right, so today I want to give a little bit of an introduction to two-dimensional crystals, and we're going to do a little bit of crystallography, just so that we get a little bit of a foothold in that vast subject, just enough so that we can understand electronic band structures in two-dimensional and three-dimensional materials. So here is now a lattice, and it's a square lattice to start out with, very simple. And this would just keep going in all directions. I get sort of this grid of points, and they're separated by a lattice constant A, both in the y direction as well as in the x direction. I can then introduce these basis vectors that generate this lattice. So T1 and T2, our book calls them. Basically, those are generating the lattice Y because every lattice location, every atomic location can then be written as a superposition of those two basis vectors. Okay, R, for instance, if I'm pointing to this particular atom, then basically I would have to take 2 steps to the right and 3 steps up, and then I'll end up at this atom, right? And so written in terms of these two basis vectors, I would say this would be 2 times T1 plus 3 times T2. But in general, I can reach every atom in the lattice that way, where M and N, okay, these two prefactors here, are integers. Yes, they're integers. Sometimes they're also, our book also calls them N1 and N2, same thing. So that's how we sort of generate the lattice mathematically with these two basis vectors. All right, so you can say that T1 and T2 are the basis vectors for the lattice in real space. Why do I say real space? Well, you guessed it, there's got to be some kind of other space to contrast it with, and the other space is called reciprocal space. Okay, so that reciprocal space is K space, also often called K space. And it encapsulates the lattice's periodicity. Just concisely stated, it is just an encapsulation of the various periodicities that the lattice displays. Okay, so again, here is my lattice. Okay, and we get sort of this kind of periodicity from top to bottom, and we also get this kind of periodicity from left to right, okay, for instance. And we can say, all right, this periodicity here, 2 pi over A, that's the wave number that's associated with that periodicity. This periodicity up, down, also 2 pi over A, and that's maybe what we could call K sub Y. Okay. And here are the particular lattice planes that we're sort of highlighting. Okay. So then we can introduce basis vectors as well. And we're going to call them 2 pi over A I hat and 2 pi over A J hat. Now, in general, we could also, okay, so just as a summary real quick, here's the real lattice, and then here's the reciprocal lattice. Okay. So in general, we could also have a lattice that is not square, right? But maybe, well, maybe sort of stretched out in one direction. So we have 2 different lattice constants. Here's a B and here's an A. Well, this formalism can handle that situation very well. Okay, no problem, because now the generating lattice for the real lattice is just T1 and T2, okay, A I hat plus B J hat. And then the reciprocal lattice, okay, is also I hat and J hat here, but 2 pi over A and 2 pi over B. So one thing that's interesting here, though, is that you see that the real lattice is sort of stretched out along the x-axis, right? So the x spacing here is larger than the y spacing, whereas when you look at the reciprocal lattice, since A seems to be bigger than B, then this magnitude here is smaller than this magnitude down here. And so actually it is a lattice that's now stretched in the y direction rather than the x direction. Okay, so that's an interesting little tidbit. All right, so now we can consider superpositions of the reciprocal lattice basis vectors, B1 and B2. And by the way, I'm using the same notation as our book. I'm sticking with the book's nomenclature here and also labels. So we're looking now at a superposition of B1 and B2 where H1 and H2 are just integers, okay, that go along with that particular superposition. So for instance, H1 being 1 and H2 being 0, okay, gives you a G that's sort of pointing to the right along the x-axis, right? It's a vector pointing to the right. And therefore, we see that we're dealing with this kind of periodicity, lattice planes that are sort of marching to the right. All right, and so look at a different set of integers, say 1, 1, okay? What kind of lattice planes would we be referencing here? Think about that for a moment. Okay, so now we have a G that is B1 plus B2. And you guessed that it's these lattice planes. You can actually convince yourself, interestingly enough, that this G that we formed, B1 plus B2, is actually perpendicular to these lattice planes. So clearly, the vector that connects this corner atom to this atom here, that vector here is not perpendicular to the lattice planes. But when you form this kind of combination, B1 plus B2, with the lattice, with the basis vectors defined like that, you can show then that that kind of G vector is perpendicular to these real planes. All right. So, but let's go back to the simpler case of a square lattice for a moment. Okay, so again, here is my square lattice, and I'm interested in these particular lattice planes. If we were to shoot X-rays, okay, into the lattice, they could actually bounce off of this set of lattice planes. Same with neutrons. If you shot neutrons at this particular crystal, they could actually reflect, if they had the right speed or the right wavelength, they could actually reflect from this set of lattice planes. So this is a real concept. It's not an imaginary concept. It's a real concept, these lattice planes. And so the question then is, what is the separation? I'm labeling it at D here of neighboring lattice planes. Well, that's not a very hard question because we know what this diagonal distance is. That's just the square root of 2 times a, right? This being a here, this being a, this has got to be the square root of 2 times a, and this is just halfway, the half diagonal, and therefore it's got to be the square root of 2 times a over 2, okay? And therefore the square root of 2 over 2 times a, fine. In this particular instance, pretty easy to figure out. But there is actually another way we can see this, namely one that argues from the G vector, okay, from this reciprocal lattice vector G, which here is clearly B1 plus B2. Okay, so it's 2 pi over a I hat plus 2 pi over a j hat. Remember, we are back to the square lattice. Okay, and so I can write that as 2 pi over a I hat plus j hat. And now I want to know what is the length of this G vector. Okay, what's the magnitude? And that's actually fairly straightforward to figure out as well, right? So that's 2 pi over a times the square root of 2. This here, the magnitude of I hat plus j hat is just the square root of 2. And so now I would like to write that as 2 pi over some distance, right? And then we see that then that distance d is nothing other than square root of 2 over 2 times a. Okay, so that's another way in which we can get the spacing here between these lattice planes is we can look at the magnitude of the associated reciprocal lattice vector, G. Okay, so just to sort of summarize then, we see that this G here is a reciprocal lattice vector, and the set of all G's then defines a reciprocal lattice. Just like R here is a real location in space of an atom, the set of all R's defines the real lattice. Okay, and so we get sort of these two lattices that go together, the real lattice and then the reciprocal lattice. So let's take a look at the reciprocal lattice. Okay, so here the spacing is 2 pi over a, not a, but 2 pi over a. And the reciprocal lattice here is generated by the lattice vectors b1 and b2, basis vectors b1 and b2. Okay, so what's nice here is that a square lattice in real space results in a square lattice in reciprocal space as well. So this here is also a square lattice. The separation is different. It's not a, but it's 2 pi over a. But it's the same type of lattice we're dealing with, the same structure. Okay. So here we are, and now I want to highlight a particular reciprocal lattice vector G, okay, namely the green one here. And I kind of would like to know, well, okay, so we can write it, right? It's minus 2 B1 minus B2. So that should be a minus, actually. Okay, so there you go, magic, I fixed it, right there, that's a minus 1, because we're going 2 units to the left and 1 unit down. Okay, so there is my G vector. Okay, and then the question is, what lattice planes does this G vector correspond to? Okay, so I'm gonna look for lattice planes that are perpendicular to this particular vector. And we see then that we get those lattice planes, okay? So these are all the lattice planes that are perpendicular to this vector G. And the question then is, what spacing will those lattice planes have, okay? So notice that these are planes that connect atoms that sort of are at this particular angle together. So, there's an infinite number of atoms on these planes, right? So there's one here, you go down 2 over 1, there's one here, you go down 2 over 1, there's another atom here, I just didn't draw it, but I could keep going, right? So here's one, down 2 over 1, that's the one at the origin, down 2 over 1, okay, I'm gonna end up with an atom there again. So actually these planes sort of contain, you can say, an infinite number of atoms. And conversely, also every atom in this lattice will fall onto one of those planes. Right? There's no atom that isn't captured by one of those planes. So, so there they are, and the question is now, what is the spacing? Well, here it might be difficult to ascertain it, but with this new trick, okay, by looking at the magnitude of the G vector, it should be fairly straightforward. So that's what we're going to do. I'm going to write the G again, and we then we're going to look at the magnitude of that vector. Okay, so the magnitude of this vector is going to be 2 pi over a, okay, times the square root of minus 2 plus minus 1. This should have been, again, a minus here. Sorry, folks. Yeah, I'm going to correct it. There, and there should be a minus. Of course, the result doesn't change because we're going to get square root of 5, right? 2 pi over a times the square root of 5. Now, I always want to write this as 2 pi over some characteristic distance. And so I get 2 pi over a over the square root of 5. And therefore, we see that d is a over the square root of 5. Okay, so that it would be the separation here. So the upshot is that the magnitude of G contains information about the lattice spacing, okay, for that set of planes. And the direction of G yields the orientation of the planes. Why? Because G is perpendicular to those planes. Okay, so G here is perpendicular to those planes, and we can see that actually quite directly. Okay, if I pick out a particular, if I'm pointing to a particular atom here that lies on this plane, I would expect then R and G to be perpendicular. If I form the dot product, I expect to get 0, and I actually do, because G here is minus 2 I hat, or proportional to minus 2 I hat minus J hat. This time I have it right. There is a minus sign in here. And then R here you see is minus I hat plus 2 J hat, right? And if I form the dot product here, and you get 2 minus 2, and that is 0. So they are perpendicular for sure. Okay. So what is sort of the bigger picture? Well, to summarize, we can say that every real lattice has an associated reciprocal lattice. Okay. This reciprocal lattice gives us the periodicities of the lattice, loosely speaking. Okay. If you want to be more precise, you can say that the reciprocal lattice is what you get if you took a spatial Fourier transform of the real lattice. And that's really the foundational definition of the reciprocal lattice. If you took the real lattice and did a Fourier transform of it, a spatial Fourier transform of it, then you would get another lattice, and that lattice we call the reciprocal lattice. Now, in this class, we won't actually worry about the precise details of how to find the reciprocal basis vectors B sub n given the real basis vectors T sub n. But our book actually does go into a little bit more detail, and this is all explained starting on page 49 through 51. Okay, and in particular, you can take a look at equations 520, 521, and 522. Okay, so there is actually a mathematical formula that allows you to go from the set T sub n to the set B sub n. Okay, now we can say that for a three-dimensional simple cubic lattice, right? So that is sort of the simplest lattice structure, crystalline structure in 3 dimensions that you can possibly think of. For that kind of lattice, then the reciprocal lattice will also be a 3D simple cubic lattice. The spacing is no longer A, now it's 2 pi over A, but it will have the exact same structure. Unfortunately, that is not true for more complicated 3-dimensional crystalline structures. So for other structures, the reciprocal lattice will not follow the same structure as the real lattice. It will not be equivalent. And this even starts with body-centered cubic and face-centered cubic. So we can still have cubic lattices, sort of a variation on cubic lattice, where you have these 8 corners of the cube, but then you put another atom in the center of the cube. Okay, and then you repeat that over and over again. That's called body-centered cubic. And it turns out that the reciprocal lattice of that is a face-centered cubic lattice, where again you have the 8 corners of the cube, but now you have additional points on the faces, the 6 faces of the cube. Okay, so a body-centered cubic crystal transforms into a face-centered cubic crystal, and it turns out that a face-centered cubic crystal transforms into a body-centered cubic crystal. So there's all kinds of weirdness going on as soon as you move away from the simple cubic lattice. So but we don't have to worry about those details in our class. That would be sort of a second semester solid state course or a crystallography course or something like that. So this really sort of goes beyond the scope of our course, but I did want to mention it here. What we want to focus in on next is the 2D Brillouin zone, right? Because that is important in terms of energy bands for electrons and the reduced zone scheme. So we have to sort of generalize the reduced zone scheme from one dimension to 2 dimensions, and that's what we're going to be looking at next. All right, thank you.